Hello, everybody, and welcome back to another lecture in Geography 341, Weather and Society. Dr. Zach Hilgendorf, and in this lecture, we're going to be talking about precipitation. There are 7 or 8 different types of precipitation that we're going to talk about, some at depth, some maybe a little bit more surface level, but this will kind of lead off of understanding clouds. In the future videos, we're going to start talking about distinctive types of weathers, things like thunderstorms, tornadoes, hurricanes, all these different things that drive weather patterns across our planet we've been learning about. And then we're going to actually start now really diving into what those patterns look like and are exhibited as is on the surface of our planet. So we're going to start with precipitation and we'll go from there. So how does air become saturated? Well, oh, so here we can look at kind of the global distribution of precipitation across our planet. So in the darkest blue, we see greater than 2,000 millimeters of precipitation annually. In the darkest red or maroonish, where I guess the orangish red color, you see less than 2,000 or 200 millimeters of precipitation. And those can happen right next to one another. We look at the Atacama and the Brazilian rainforests, or the Sahara and kind of Central Africa, or the Tibetan Plateau and the Brahmaputra Delta, and all these different regions. You can have very rapid fluctuations in precipitation. We learned what drives some of those things, like orographic lifting or other cooling of the atmosphere. As long as there's some type of change, there can be condensation and cloud formation and hopefully precipitation. And that's what the video is going to focus on here. Is our different aspects of precipitation. First off, processes of precipitation. Um, so what is precipitation? Well, it's just water, liquid or solid, that falls from the clouds to the surface. That's a pretty easy definition, right? Well, what do you need for precipitation? First off, large cloud particles, liquid or solid, whatever. High terminal velocity, so the ability to return and not be held buoyant by different air masses or forces. The ability to fall to Earth before evaporating or sublimating. Effective mechanism for cloud particle growth. So if we look at a little diagram here, we've got our little parcel. We talked about this in a few videos back. It's got a dew point of 21 degrees Celsius and air parcel temperature of 25. And 500 meters up with the dew point lapse rate and dry adiabatic lapse rate, we cool to 20 degrees Celsius. Okay. So now we're at the lifting condensation level. We talked about that before. You should be well familiar with that. That's oftentimes our cloud base and where our clouds start to form. So if we zoom into that lifting condensation level, you see at the lifting condensation level, we've got these condensation nuclei with a diameter somewhere around a micrometer or so that are allowing water to condense on them. And as that air continues to rise and you have more and more condensation, you can get cloud development. So by about 50 meters above the lifting condensation level, you can have numbers of droplets in the billions. So droplets per cubic meter in the billions. So if you think of how much space each one of these little particles takes up, and how many condensation nuclei that require, you can kind of get an idea for how what we see exhibited as clouds start to form. So if you think, 10 micrometer droplet, volume of 524 cubic micrometers, 1 micrometer droplet has a volume of about 0.5 micrometers or cubic micrometers. A 20 micrometer droplet has a volume of about 4,200 cubic micrometers. And we can keep going up. 500 micrometer droplet, the larger ones, can have a volume of 65 million micrometers, cubic micrometers. So how do cloud droplets grow into rain droplets? How do you get that out of the cloud and falling onto the earth? Well, First one, things like collision coalescence processes. So basically what you have here is a collector drop that is colliding with smaller drops. Due to the compressed air beneath that falling drop, there's an inverse relationship between collector drop size and collision efficiency. So as they get larger, they can push some of that out of the way uh, rather than absorb it with the smaller collector drops. Collisions typically occur between a collector drop and uh, fairly large cloud drops. Smaller drops are pushed aside. You can see in this example here. So in the left, we've got our collector drop, not yet ample size to start pushing some of that away. And in that right one, we are pushing some of that away. The smaller ones there may be absorbing some of the other ones. Uh, when collision occurs, drops either bounce apart or coalesce into a larger drop. Coalescence efficiency is very high, indicating that most collisions result in coalescence. This isn't always constant, but in general, most of your collisions are going to result in water being absorbed into that particle or that growing drop. Collision and coalescence together form the primary mechanisms for precipitation in the tropics, where warm clouds dominate. In warm clouds, clouds formed in temperatures above freezing, 0 degrees Celsius, the collision of minute cloud droplets create these larger droplets. This process we just established called coalescence. Coalescence helps to break the equilibrium of the atmosphere, which keeps minute droplets suspended in the clouds. The droplets which combine together become large, which sometimes make them too heavy for cloud updrafts to keep up. It's a game here where can we exceed the buoyancy of that droplet? Or if we can exceed it, we will fall through and we'll precipitate. If not, we'll just be continually held aloft within the clouds. So as these droplets fall through, they merge with other droplets, that coalescence that we talked about, making them even larger. Sometimes they'll bounce off one another, and it's leading to things like charging. So different electrical charges, if you think about that, kind of that generation, that friction generation of things like lightning. So if the air underneath the cloud is moist, the droplet will reach the ground as drizzle. If it's extremely high above the ground, the droplet will likely evaporate before reaching the surface. So these are in warm cloud situations. In cold clouds, precipitation-sized particles formed by what we call the Bergeron process. When the temperature in a cloud is between 0 and 40 degrees C, there exists or negative 40 degrees C, pardon me, there exists a mixture of ice crystals and supercooled water droplets. So that supercooled water remains liquid even though the temp is below freezing due to kind of pressure and some other scenarios. So the reason for this is that they don't typically freeze until the temperature drops below that negative 40 unless they contain a special type of cloud condensation nucleus called an ice condensation nucleus. Oftentimes there's a scarcity of those ice condensation nuclei in the atmosphere. Therefore, when the in-cloud temp is between 0 and negative 40, it's mostly supercooled water rather than liquid. This observation is important, again, in that formation of lightning and hail. So here we can see the Bergeron process. Ice crystals grow as water vapor deposits onto the crystals, while the supercooled liquid water droplets evaporate. This occurs because that saturation vapor pressure, which we talked about a few videos ago, for water is higher than the saturation vapor pressure for ice. We looked at that divergence of that curve, looking at supercooled water versus ice when we're looking at saturation vapor pressure and starting to calculate relative humidity. The result is that ice crystals continue or grow large enough to begin falling from the cloud. On the way down, they may grow even larger as they contact supercooled droplets of other ice crystals. So aggregation, which we see in that bottom one, is the joining of multiple ice crystals through surface water bonding, building ice crystals to the point of overcoming these updrafts. We can see a couple examples here. Then we've got riming, and riming is just the process by which liquid water freezes onto ice crystals, producing rapid growth. We'll talk about riming towards the end in one of our examples of precipitation. But we can see that, you've got a snowflake here, and then we can see that rhyming occurring on the snowflake. So notice it kind of loses that, I guess you could call it, loses the beauty, or loses that crystal clear nature, and kind of becomes this fuzzy aggregate that we see here. We can see some examples of cool clouds here. So we've got 0 degrees Celsius there, negative 40 degrees Celsius there. Then you notice, here in this cumulonimbus cloud, we start seeing that wispiness around the edges as we're converting maybe to ice crystals rather than that water or supercooled water droplets. Let's see some examples of more just precipitation here. Then moving in the types of precipitation, we've got a number that we're going to go through. First off is rain. So rain and drizzle are just defined as any falling drop of liquid that has a diameter greater than 500 micrometers, or half a millimeter. Rain can either be showery or continuous. Showery rain comes in the form of cumuliform clouds, continuous rain in stratiform clouds. The atmospheric significance of showery rain is that it shows that the atmosphere is unstable in the lower atmosphere. For continuous rain, it shows that the lower layers of the atmosphere are stable. So showery rain, think cumuliform clouds or cumulus clouds, think instability. Stable, longer term rain, think stratiform clouds, think atmospheric stability. Drizzle is defined as any falling drop of liquid water that is less than half a millimeter. Drizzle only occurs in stratiform clouds, and it lets meteorologists know that the atmosphere is stable. You can see some examples of that here. Here we can see a temperature profile. So rain is obviously liquid water that hits the ground, but because the air temperature in clouds is often well below freezing, it's common that rain on the surface left the cloud as snow, especially in the winter before melting on the way down to the ground. So evidence for this can be observed in mountainous areas when the same storm systems produce snow in the mountains and rain in the valleys. Depending on a complex combination of microphysical processes and larger scale atmospheric conditions such as relative humidity, updraft speeds, raindrop sizes, range from the small drops, drizzle and mist, to the larger drops that we talked about. So here we can see kind of a typical temperature profile. So while we might have been right at or right around freezing near the cloud, we kind of warm to maybe ambient surface temperature by the time we hit the surface. And that you can see kind of in this example graph on the right here. Sometimes here's our example where you've got snow and for that first portion, and then that melts kind of at this point here and falls as rain. So those are the two kind of examples where you get rain falling onto the surface. So here's a question: what shape are raindrops? Because we think of them oftentimes as this nice teardrop shaped, right? Nope. It's kind of a common misnomer. So typically what's happening here is you've got a drop around maybe 2 millimeters. As frictional drag increases, these raindrop shapes change from a round bead to actually kind of a mushroom based off of things like surface tension. You can see that here. So the drops eventually start to flatten. As frictional forces continue to act, you see that mushrooming occurring. Sometimes that can lead to drops splitting when the frictional drag force overcomes the surface tension forces within the water. Splitting ensures a maximum drop size of about 5 millimeters and the continuation of those collision and coalescence processes that we talked about before. You can go check this video out if you want to learn more about kind of the anatomy of a raindrop. Next, we've got snow. So in the wintertime, when freezing levels drops to a lower extent than in the summer, precipitation is able to fall to the ground as snow. It can usually fall 1,000 feet and above freezing temperatures before melting. Therefore, one would want the freezing level to be less than 1,000 feet if they wanted to see precipitation fall as snow. When snow falls from cumulus clouds, they're known as flurries. Flurries usually only produce a small amount of precipitation. On the occasion, flurries will become intense. This is known as a snow squall. So there's a couple different types of snow. You've got grains and pellets. So grains form uh, as smaller opaque grains of ice. They are essentially solid drizzle. Um, they tend to fall in small quantities from stratus clouds and never in the form of showers. When a snow grain strikes a hard surface, it doesn't bounce or shatter. Snow grains are a good indicator of atmospheric stability. Pellets, on the other hand, are those white opaque grains of ice around, a tenth to 2/10 of an inch. Snow pellets resemble snow grains but they're much more brittle. They'll break when they hit the surface. Snow pellets usually fall as showers from cumulus congestus clouds. Whenever a snow pellet falls from the sky, it shows that the atmosphere is unstable. So again, instability with cumulus clouds, stability with stratus clouds. Just kind of keep that in mind as you're going through. So here we can see that example where we never, even though we might get to around freezing, we start well below freezing and we stay freezing by the time we get to the surface. Some fun pictures of snow, although if you're watching this when I originally recorded it in February, you're probably sick of that by now. Here as well. Next, we've got graupel. So this is an interesting one. So when ice crystals fall from the sky, they collide with these super cool droplets. We talked about that, but this causes those droplets to freeze on contact, leading to accretion or riming. And riming matter is now what we call graupel. So you have that riming that occurs onto the ice crystals, and then as it kind of condenses, that fuzziness that we saw in that picture earlier, that's what we call graupel. So as the graupel falls, it tends to splinter up into tiny ice particles as it collides with other cloud droplets. So these droplets then turn into more graupel. The process continues. So we can see an example of it here and here. It's often mistaken and referred to as hail, but it's not. It's crisp, easily crushed, and it bounces when it lands on a hard surface. So squalls of graupel occur primarily during the fall and spring months as a result of, here, extreme instability in the Great Lakes regions. Here we can see that riming process a little bit more refined. So you got to start out with a, ice grain, and then the riming occurs in that middle one, and then you see kind of graupel in that right one there as well. So it's not hail. Hail forms through a different process that we'll talk about here, but it can grow to a pretty sizable extent. Next, sleet. Again, not hail. Sleet begins as ice crystals which melt into rain through a mid-level temperature inversion before solidifying into colder near-surface air, or in the colder near-surface air. So sleet is less prevalent than freezing rain, and sometimes we call it frozen raindrops that bounce on impact with the ground or other objects. Sleet is more difficult to forecast, unfortunately, than freezing rain because it develops under more specialized atmospheric conditions. So you've got cold, warm, cold again. It's much less troublesome than freezing rain because it's easy to see and it's already frozen before hitting the ground. Whereas things like freezing rain freeze as they hit the surface, which is much more problematic. So here we can see, is it sleet or is it graupel? Because the two can be kind of confused. So sleet is liquid precipitation that freezes before it reaches the ground. Graupel are snowflakes that collect supercooled water droplets on the surface. So definitely want to know how to be able to distinguish between those two. You can see an example here of sleet. So it starts as snow until we get to this point. It's rain as that snow melts, and then it's freezing again. So there's some type of temperature inversion in the middle portions of the troposphere that's leading to this type of event. You could see maybe along a warm front that would be pretty typical spot where you would see sleet. So you've got your cloud riding up this warm front here. Here's our colder air mass down here, our warmer air mass up front. So the cloud obviously is much colder. It's 0 degrees or less. We have this line of melting, so it melts and then it refreezes again once it encounters that cold air near the surface. Next, freezing rain. Freezing rain is basically what happens if a water droplet touches the surface and immediately freezes. So basically, when water droplets fall through a deep layer of cold air, they fall to the ground as snow. When a freezing layer beneath a cloud is shallow, there's not enough time for that raindrop to freeze before it hits the ground. Then it instantly freezes when it does hit the ground. Now, this can also happen on planes, which can be an incredibly dangerous event where the plane gets so heavy that it has to either crash or land rapidly. We can see examples of that here. When you hear news of an ice storm, it's freezing rain. That's what we're talking about. Ice storms can be some of the most devastating of the winter weather phenomena that we experience and are often the cause of things like automobile accidents, personal outages, or power outages, personal injuries. And ice storms result from the accumulation of freezing rain. That's so super cool that it freezes upon hitting the surface. So that surface that we're looking at in that bottom left image is completely frozen over, as is this. We actually, I think, saw an example of this earlier on this winter. So I'm recording this in the winter of February of 2023. So I think we had a good example of this that was pretty devastating for some of the trees in the area. So freezing rain develops as falling snow encounters a layer of warm air deep enough for the snow to completely melt and become rain. As the rain continues to fall, it passes through a thin layer of cold air just above the surface and cools to below freezing. So you might get this super cooled air or a super cool droplet that isn't yet frozen. However, the drops themselves don't freeze. When the super cooled drops strike the frozen ground, as we mentioned before, they instantly freeze, forming a layer of thin ice. It can paralyze a region within a matter of a couple of hours. So again, these are incredibly dangerous phenomena. Here you can see an example of where you might have kind of freezing rain. So freezing rain is when sleet is over on the right here, when there's ample space for that to freeze again, that drop that has melted to freeze again. Freezing rain occurs over here when that drop that's melted doesn't have time to freeze again and hits the surface and then freezes. So that's the distinguishing factor really between sleet and freezing rain. It's that distance to allow that droplet to freeze again, or so that it's so super cool that it freezes on impact. We can see examples of freezing rain here again, and here as well. All right, moving into some of the bigger ones, things like hail. Hail is a really interesting one. So basically, you've got pieces of ice that are either transparent or partially opaque, range in size from small peas to golf ball sized hail and sometimes even larger. Hail is produced by cumulonimbus clouds. You need that rapid and strong updrafting to occur to keep these particles buoyant. Hail is a direct indicator that the atmosphere is very unstable and that thunderstorms are present. Here you can see that phenomenon. So what you've got going on here is hail forming as concentric layers of ice build up around graupel. It's formed as graupels carried aloft in these updrafts. So you can see kind of these water droplets moving up, hail beginning to form, and then circulating and continuing to circulate. So the more it has the ability to circulate, the more layers you're adding onto it. That's how you get that concentric layering. Hail then plummets, but if caught by another updraft, the process repeats itself. The ultimate size of the hailstone is determined by the intensity of the updraft. Most hail events in North America are occurring over the Great Plains region. So you can see how it's described as far as size. So BB size is, 0.6, less than 0.64 centimeters or a quarter of an inch. Softball is greater than 11 inches basically. Hail is often occurring in these big cumulonimbus clouds, like I said. You're not really going to see them you're not really going to see them in any other scenario unless if you have these big cumulonimbus systems. Some examples of hail here and here and here. Really large hailstone right here. The largest hailstone recorded in this area was almost 2 pounds, 8 inches in diameter. Typically, the most incidences of hail, as I mentioned, happen right over the Great Plains region here. So Colorado, Nebraska, Wyoming area. See some more examples of it here. You can see really well in these two pictures those concentric rings that are forming as it's been kept aloft in the atmosphere, and you're adding more and more layers of condensation and freezing that occur on these hailstones. Finally, we've got occult. So on Inselbergs and mountain masses within the tropics, the summits are frequently covered in cloud in locations where orographic uplift of moist air is sufficient to cause condensation. If the upper slopes are covered in forests, the surface of the leaves and branches act as collectors for the condensed water vapor. This phenomena is referred to as occult precipitation because it does not relate to any rain-making process in the cloud itself, and rain gauges placed outside the forested area will not record any rainfall. It's basically just precipitation condensing onto trees and then precipitating from just so much condensation within the vegetation or on the tree. In areas like this or this, where you'll see that happen a lot in the rainforests and the areas like the Pacific Northwest, you'll see this happen a lot, and there as well. So you can see that rain droplet condensing there in that last image on the bottom right. You can see it here as well. So if you had a rain gauge over here, it doesn't have anything condensing, but if you were in here, you would. So that's our occult phenomena. And here you can see in the redwoods that occurring. And the last one we're going to talk about is virga. So we also call this fall streifen, fall streaks, or precipitation trails. They're basically wisps or streaks of water or ice particles falling out of the cloud but vaporizing before they reach the Earth's surface. Typically, you see this as kind of a hooked form in which the streaks descend nearly vertically just under the precipitation source, but appear to be almost horizontal at their lower extremities. Such curvature of virga can be produced by strong vertical wind shear, but ordinarily from the fact that droplet or crystal vaporization decreases the particle's terminal fall velocity. So under some conditions, it's associated with dry microbursts, which are formed as a product of vaporization. Typically, you'll see these trailing from altocumulus or altostratus clouds. They're also discernible below the base of high-level clouds like cumuliform clouds, from which precipitation is falling into a dry subcloud layer. Here are some examples of that. Notice that hooking that's pretty evident going through here as that terminal velocity reduces and they're kind of being blown off course based off of whatever patterns are set up just above the surface there. And we see that here as well, kind of hooking this way. So there we are. We talked a bit about global precipitation distribution, what is required for precipitation, how precipitation forms, and the variety of different types of precipitation. So in the next video, we're going to start talking about some global patterns of atmospheric circulation, what drives all of these things to move about, and then we'll get into a bit more of the interpretive aspect of things like thunderstorms, tornadoes, hurricanes, mid-latitude cyclones in general, etc., etc. So hope you enjoyed this video, and we will see you in the next one. Thanks.